Welcome back, everyone. Today I'm talking to Murtaza Jafry regarding interacting fractons in 2 plus 1 dimensional quantum field theory. This will be a mathematical discussion, but it will also be quite focused on actually the physical aspects of things and fractons in particular. I hope you enjoy that. Before we jump into the details of that paper, would you mind giving a brief overview of fractons? I think that would be a good place to start. What are those?
Yeah, right. So, fractons are, it's a very rich topic of physics research, but fractons in general can be thought of as these kinds of quasi-particles that are immobile as individual particles. So typically when we think of particles in nature, we think of electrons or elementary particles like muons, neutrinos, and so forth. Generally, these particles are dynamical by themselves, meaning that they can move, they have some kind of translation invariance, and move independently. Now, quasi-particles are kinds of particles that have these were developed. This notion was developed quite a long time ago in the many in the early formulations of condensed matter physics and everything, where these are particles that have particle-like properties but have novel dynamics, like fractional charges possibly, or some kind of fractional quantum numbers. These properties had arisen later on, and so these particles began to be known as quasi-particles because they have quasi-like properties of
Mhm.
conventional particles that we understand. Uh, but fractons are these kinds of quasi-particles because not because they are not only can they have these novel fractional charges and these other fractional properties, fractional quantum numbers, but they also principally are non-dynamical individually. And what does that mean? As I had said, particles can move independently typically, as we understand. They can move up, they can move down, they can move in three-dimensional space, but fractons can only move in terms of dipoles. And this is where this is a strange component of what how we try to interpret fractons, which is that a dipole, if you think of an electric dipole, you think of a positive and negative charge, and the electric dipole is the charge separation between them.
Mhm.
Now, in the case of the fracton, the dipole itself will move, meaning that the two individual fractons that we consider will move as a bound state effectively. So instead of having this individual motion that you would expect for conventional particles, you'll have this bound state motion instead. Now that
Mhm.
greatly constrains your dynamics in terms of if you try to think of fracton dynamics or these kinds of dynamics of these particles, if you can only move as a bound charge, it gives you it limits the amount of stuff you can do compared to more conventional particles, but it gives you this more new emergent kind of physics that is very interesting to analyze. And so purely this,
Do you have an example of how it's significantly limited by that fact? Like, let's say you have two particles and they have to move with some form of the way I take it is they have some restraint, let's say relative to each other, not
yeah,
relative necessarily to the other system, but to each other.
yes,
Assuming you would have like some kind of like assuming you had some medium where you have flexibility of individual particles, so long as there is not this constraint that ties two of them together.
right,
How is it then significantly different to have two tied together? If you had, let's say, the possibility of motion in the original formulation,
right.
having like in all directions, how is
Mhm.
that significantly altered by the fact that two of them are tied together in some way?
Right. So the tied together part is if you consider them as a bound state itself, then sure, you could say that, well, the bound state has translation invariance and it can move like a conventional particle. And that would then
Mhm.
mean that the two particles can then move in this unique way. And so in that, if you view it in that circumstance, in terms of a global system, then yes, that would be the case. But typically, how we're more interested in looking at these systems is trying to understand the symmetries of the particles in themselves, right? So the way that physics is generally done in the context of field theoretic techniques or these lattice constructions is we can try to consider all the kinds of symmetries that may be present in this specific kind of system for this individual particle, and then try to assess what are the potential kinds of interactions we can have, or the potential kind of kinetic terms we may have, and that restriction of the individual particles becomes apparent when you have that actual action formalism. So if you consider a collective system and you consider just from a physical standpoint, yes, it is possible that you could reproduce the same kind of dynamics you may have as a bound state of an individual particle moving. But in the case of actual physics, in terms of writing down the action and writing down its equations of motion, this restriction of bound states greatly impacts how these systems will move. And that's
Okay.
where it becomes apparent, especially in terms of the physical consequences of these bound systems, where you actually see this difference.
Mhm.
Does that make
Okay.
sense?
And Yes, that makes perfect sense. And there are some different kinds of fractons as well, right? That it's sort of an umbrella term for multiple different ones. I know of charge fractons and aeon fractons, for example. I think those are two different versions of it.
Right, right.
Could
So
you
yeah,
could you shed could you shed some light on what different instantiations there are, let's say, and then also what you focused on particularly in this paper, or whether what you focused on is more of a generalization that could apply to any of them?
right, right. So exactly as you said, fractons is really an umbrella term in many ways. It's basically any system, in the broadest sense, that doesn't have this kind of individual translation invariance and that can only move in these bound states. And so typically when these systems were first introduced, there are many different contexts in which they could be applied. One case that's of particular interest is in these lattice constructions. So physics, we're interested in in condensed matter specifically. Many systems
Hmm.
we like to consider on a grid effectively. This is known as a lattice in physics, in which you have individual point sites, lattice sites, which are connected by links, and these links are supposed to be representative of some kind of system that's relevant in condensed matter. So, for example, a solid or other kinds of materials that might be important. And the physics of these systems can be quite unique in that they can have some kind of spin associated with them, or they can have some kind of interaction associated with them. And you can have an array of different kinds of systems that have these kinds of characteristics. And the way where you see fractons in one instance is in this lattice system, in which if you create excitations on these lattice sites, in that which is again a very unique definition, in that you can consider these lattice systems as a quantum system, and so they have basically a different kind of spectrum. You can have eigenstates and eigenenergies of these systems, and in that context, what you can have is quasi-particle excitations. You can have energy excitations on these systems that are reminiscent of particle dynamics. And this is what gives this notion of quasi-particles, in that they're not elementary particles as you would interpret them as electrons or so forth, but they are these particle-like excitations that have properties of particles, but are not particles explicitly in the conventional sense. And in this case, you can actually see fracton-like dynamics, in that if you have two quasi-particle excitations, you'll find in this kind of lattice system, you'll actually find this constraint of that these two quasi-particles can only move as a bound state, and that their dipole is the only translation invariant system, not the individual excitations themselves.
Hmm.
So that's one
When we
such.
say
Sorry, go ahead.
Mhm. When we say that this is an excitation in the lattice in some sense, is the excitation bound to some specific property of that lattice? Like, let's say there's some part of it that where this energy excitation is localized, and it can transition from one part of the lattice to another, but it's nevertheless tied to one particular feature, let's say, of the lattice. Is that the case, or is it? Um,
Right. So there are many different kinds of systems. So one system you can say is that you have these localized excitations that only occur at one part of the lattice.
mhm,
Um, but you can also consider, and again, this will also inherently depend on the topology of the lattice itself. So you can have uh, lattices that are uh, basically have non-trivial boundary conditions, in which can have von Neumann boundary conditions or Dirichlet boundary conditions, or they can have boundary conditions of a torus, so they can be continuous and they rotate on themselves. And in each of these cases, you'll find that these kinds of quasi-particles might have different motion. So they could be localized in one area, but depending upon the system itself, they could traverse the entire lattice itself. But
mhm.
that would be heavily dependent upon the kind of lattice system you're considering, and the kinds of interactions you're considering, and more importantly, the strength of the interactions you're considering as well. So
Okay.
it's highly dependent on the lattice itself, but you can have both instances occur.
Mhm. The reason for my previous question was I'm trying to understand a little bit better why fractons are particularly relevant for lattices. Like, what is it that ties those two notions together? I would expect that it has to do something with the rigid structure of a lattice, and that the excitations, like that, these kind of constraints only arise there. Is that the cause, or is it more that for in solid state physics, that's where we can utilize the that's where we can say something intelligent about these systems. Like, do fractons appear in, let's say, gases or other forms of matter as well, or is the reason why we're considering solid state physics and all of this just simply that fractons really only do arise in those kind of systems?
Right. Yeah. So I think your former answer was right in that most of the time these fractons occur in these kind of lattice systems. So in general, gas-like systems, I don't know any particular example in which fractons might appear. Because again, conventionally, when we consider translation invariance, these particles can move and have standard translation. And so typically this bound nature to them is very particular to specific kinds of systems. And they are most prevalent in lattice systems. But more recently, there have been, I think, works where people have been trying to see if there are kind of fracton-like properties in other kinds of systems, in elastic systems or systems outside of just the lattice constructions. But the one that are most prevalent and I think at the moment most well understood are in the context of these lattice contexts.
Okay. Okay,
Yeah,
cool. So maybe we can have a look at the introduction to the paper. So in
sure.
the abstract here, you just summarize what the purpose is. So you analyze in perturbation theory a theory of weakly interacting fractons and non-relativistic fermions in a 2+1 dimensional QFT. And then this is what I want to discuss next. In particular, we compute the one-loop corrections to the self-energies and interaction verdicts and calculate the associated one-loop renormalization group flows of the coupling constants. Can we maybe start with one-loop corrections to the self-energies?
Mhm.
So if we start talking about the self energies, why do you choose to study that? Why is that a relevant property when it comes to describing these systems?
Right. So to break down what we actually did in this paper, so as we had discussed, these kinds of fractons appear in the context of lattice systems, but lattice systems are not are very hard to analyze conventionally because the way that typically we try to analyze systems is in the from the standpoint of quantum field theory, which is basically a field theoretic definition, a continuum field theoretic definition of particles, elementary particles, and it's the standard paradigm that has been used to explain all of particle physics and more
Mhm.
and condensed matter physics. And so in this paper, what we're trying to effectively do is try to construct a continuum field theory, specifically an interacting continuum field theory of fractons. So continuum field theories of fractons have been analyzed, trying to describe the low energy dynamics of these kinds of lattice systems. So as I had
Mhm.
discussed before, these fractons appear in these lattice systems, but something that people are particularly interested in is in the case of when the lattice spacing goes to zero. So in these lattice sites, we have these kinds of separated lattice points, and these sites are interacting with some kind of spin or some other kind of dynamics. But one particular case that we might want to analyze is what happens if we squash the lattice spacing to zero, and we have a continuum field theory. And the
Mhm.
idea is that this is a highly non-trivial problem because conventionally lattice field theories have a whole bunch of issues that arise when you try to compactify them. And this becomes abundantly apparent in the case of fractons. And so what we were trying to analyze was that the initial continuum field theory that were constructed for fractons, had a very non-trivial structure to them. And what we were trying to understand is, could we try to consider an interacting version of this theory, a very simple theory of fractons coupled to, say, fermions, some non-relativistic fermions, which are another species of particles, and see if we can use standard techniques of quantum field theory to try to analyze its dynamics.
Mhm.
This is where this first sentence. Sorry, go ahead.
No, I was just going to say, is there, for the interaction between these, is
Sure.
that significant? Do we know whether it's significant? Or, like, do we have a view of how significant the interaction is with fractons and other particles in particular? Is that mapped out in some way, or are we simply speculating there at this point? We don't necessarily have like experimental validation
Right,
for
right.
how strong the interaction is. Like, how mature would you say the field is in that regard?
Right. So experimentally, I think these things have not been measured explicitly. At least I don't think there's been any kind of robust experimental evidence to show these things, especially the continuum side. So at the moment, it's much more of a theoretical construct to try to have some consistency checks to show
Mhm.
that there is consistency between the continuum theory and the lattice theory. Because from
Mhm.
our understanding of these kinds of lattice systems is that there should be some kind of continuum model that is present at when the lattice spacing goes to A. In the case when
Mhm.
there isn't, that leads to an inherent contradiction because our notion of renormalization and the idea that when lattice spacing gets closer to zero, there should be some kind of continuum-like field theory that should exist.
Mhm.
Our standard understanding of quantum field theory and lattice field theory more generally. And so at the moment, it's much more of a consistency check to make sure that our current paradigm of these field theoretic constructions is indeed consistent.
Okay. Okay, understood. How come you're specifying that these are weakly interacting? Is there a strongly interacting version of this, let's say, or like what is the reason for weakly interacting seemingly being a let's say a priori decision on the modeling approach, or am I misunderstanding the way this is written in the introduction?
So in this case, so we weekly, I guess you could say is in the actual theory we consider itself, we consider an arbitrary coupling between the fermion, this non-relativistic fermion, and the
Mhm,
fracton itself. Um,
mhm,
it's weakly coupled in the sense that we can apply perturbation theory to it. So in quantum field theory, this paradigm that I had been discussing. They're historically one of the greatest tools that people have used to try to analyze these systems is known as perturbation theory, meaning that you take a series-like expansion in the quantum field theory to try to get an approximate result of some relevant dynamics of the system. And this perturbation theory, this kind of series expansion, if you remember in calculus class, you take something like a Taylor series. These Taylor series, if you take a truncation or a leading order expansion, is only true in the case when the expansion parameter is very small.
mhm,
And typically, the expansion parameter in these quantum field theory systems is the coupling interaction between the fermion and, in this case, the fermion and the fracton. And in
mhm,
the case when it's weakly coupled, meaning that the coupling strength between the two particles is small relative to the relevant energy scale, then you can indeed do perturbation theory or this series-like expansion to try to get approximate results for the
mhm.
physics. And so
Okay,
in the yeah, sorry, go ahead.
so the discount factor, if you will, in the perturbation theory expansion is inherently tied to the strength of the interaction, and
That's
so we're limiting the scope to weakly interacting fractons because we don't have a solid, let's say, mathematical formalism to describe the systems where it's not weakly interacting. Is that
right, right. So, and this is actually a problem in just general quantum field theory as well, because if you have a strongly interacting system, say something like quarks, the strong interaction is a very
Mhm,
common example where in the case where the regime is very strongly coupled in like confining phases, for example, you cannot apply these conventional perturbative techniques, and so you have to rely on more non-perturbative techniques to try to understand the physics. And so as a first check, typically what people do is that if you want to analyze, say, an interacting theory, you try to use this perturbative procedure to try to establish some basic ideas and see if you can extrapolate that to non-perturbative aspects of the physics. And in this paper, we actually do that, where we show that if you sum all of the series terms together, we can actually get some very unique non-perturbative results about the underlying physics.
mhm. Okay, great. If we move over to the second term in the introduction here, it's interaction verdicts. Would you mind describing what that is and painting a bit more background into
Yes,
that?
yes. And sorry, and also to your original question of what these self energies and these loop corrections are. So
Yes.
in quantum,
Okay. Let's get back to the first. Yeah.
right, right. So sorry, there's a lot of build up to these ideas, which is in quantum field theory. One of the ways that we analyze these kinds of perturbation theory is through the notion of Feynman diagrams. So Feynman diagrams are very, I think everybody has some implicit notion about them, which is they're basically this kind of particle diagram representation of these kinds of interactions. And so basically what they represent in the actual formalism is that every term in the series expansion that we might find in terms of this perturbation series that I was talking about can be represented diagrammatically by these Feynman diagrams. And so
Mhm,
basically what this physics allows you to do is effectively represent if you can write down these Feynman diagrams directly and specifically the relevant diagrams to every order in its expansion, what you can do is basically calculate all of the relevant physics from those diagrams. So it's a very concrete, clear diagrammatic representation of what we're interested in computing.
mhm,
Now, the specific terms in the thing that were referenced, say, as you said, a vertex correction and self energy, these are very specific kinds of diagrams that are relevant in the kinds of physics that we're interested in.
Okay.
Specifically,
So one follow-up question on that.
sure.
So the specific diagrams that we're considering are inherently linked also to the quantities that we're describing. These are the Feynman diagrams, if you will, are not general descriptions of the system that we then use to derive these quantities, but rather you pick a quantity first, and then there's a corresponding Feynman diagram, let's say, or a Feynman diagram expansion that you would, let's say, establish and then calculate based on the equations that are associated for that specific term.
That's right. That's right. That's exactly right.
Okay.
So exactly as you had said, these two Feynman diagrams are intimately connected with the actual theory that you're considering. So in this particular diagram that you have on the screen, what you have are you have four lines effectively. You have these dotted lines, which in our case represent the particle of the actual scalar, which is the fracton. So it's called a scalar because the field actually is one-dimensional. It's three-dimensional, but it has no vector representation. In this case, the solid line, the line in this bubble that you see, is the fermion, which is the second species of particle that we're considering, describing this non-relativistic motion of the actual fermionic particle across the scalar itself. Now, the interaction, the vertex that you see between the dotted line and the solid line, the two interaction vertices you see right there, these are known as, in this diagrammatic representation, these are the interaction vertices that describe the interaction between the fermion and the scalar, or the fracton. So the fracton and the fermion, this is the coupling site that you see present in the diagram. Now, the reason why this is important is because once you have the theory, and you have this diagram itself, this is known as a first order diagram because there's only a single loop associated with it. In this diagram, all we have to do is write down the diagram itself and simply look at the relevant lines and the relevant interaction vertices, in the case here, the two vertices and the four lines. And from there, we can construct, using this procedure of Feynman diagrams, compute the relevant first order term that's present in this kind of series expansion for the quantum field theory. And in the exact computation that we do in the paper, you can see that it actually corresponds to a specific kind of integral that's present in the first order expansion of the series.
How does one go about finding, or like, what is the cookbook recipe, so to speak, for generating one of these diagrams? So we have some interaction that we would like to study first, and then the first step of this process is we construct the diagrams. From the diagrams, we get the equations, and then we can calculate whatever we want. But how do we actually get to these diagrams? My understanding is there are multiple first order diagrams for, like, if we're considering generic systems as well. So how would you mind shedding some light on how we actually get those?
Yes, exactly. So you're right that there are many different diagrams that can contribute to first order and higher orders as well. So the first thing you do as a first step is write down the Feynman rules. Now, what are the Feynman rules? As I had mentioned before, once you look at these diagrams, what we're interested in writing down are these lines which represent propagators. Now, propagators are basically this notion that a particle can propagate from one position in space-time to another position in space-time. And in this case, this very specific propagation is represented by what is known as a Feynman propagator. And this has a very specific mathematical representation in what is known as position or momentum space. So in quantum mechanics and quantum field theory in general, you can represent these propagations in terms of a very specific representation of either momentum or position. Second, what you can do is now define these kind of interaction vertices similarly either in position or momentum space. By convention, momentum space is chosen because momentum space gives you a very clear and concrete way of computing these diagrams, or specifically these kinds of momentum integrals that arise in them. And so as a general algorithmic procedure, the way you would do it is you would write down the Feynman rules, you would write down the other relevant propagators and their equations in momentum space, you would write down the interaction vertices in momentum space, and then from there you can then compute any relevant diagram. Now, the way you would get the diagrams, the second part of your question, which was how do you distinguish between, say, a first order diagram and a second order diagram, this is known as trying to figure out how many loop momentas you have. So in the case where you have a single loop momenta, and again, what loop momenta means is that in this bubble diagram, in this particular example, you have effectively what physically is happening is a scalar, a fracton is coming in. This fracton splits into two different fermions, a non-relativistic fermion going in one direction and an opposite non-relativistic fermion going in the opposite direction. Then these two particles recombine and then go back to becoming a scalar. Now, by momentum conservation, what happens is that these two particles can have any amount of virtual momenta, meaning that these create two virtual particles and that you cannot measure them. They are called virtual because you don't measure them experimentally. They're these kinds of internal processes, but they can have any kind of momenta propagating through these bubbles in this kind of bubble-looking diagram. And so if you only have any one loop momentum in this kind of bubble, then you know it's a first order diagram because any other diagram above, if you have two loops or three loops, you know that would contribute to the second and third order diagram. So any one loop contribution, any one loop integral that's present that you could possibly construct that are homeomorphic to each other, meaning that you cannot deform them in a way that is equivalent because if you move these lines up, they're equivalent diagrams. Any homeomorphically distinct first order loop momentum diagrams all contribute to these first order contributions. And those are the diagrams that we will consider in this analysis. And any diagram above that, any two loop or three loop would contribute to these higher order diagrams.
Okay, and if we look at a bit further down the paper, I think you also have an additional figure that this one.
Yes.
I was thinking about this one and whether or not this actually tells us something about like, is this somehow the ground expansion, let's say, of the perturbation theory, or am I misunderstanding this figure altogether? So if we're bringing it back to talking about perturbation theory in general, we're saying that that's similar to a Taylor expansion, and then that you have some form of base term, and then that you have higher order terms that add to that. And given that we have weak interactions, those are exponentially decaying according to the size of that interaction. Sure. Does this one somehow represent the like base expansion, let's say, or the base term, or what is this figure?
So this term is actually another one loop diagram that you see. So here what you see is similar to the diagrams that you had shown above. In this case, what's happening is that instead of having a scalar just come in this case, the fracton come in and split into two virtual fermions, what you now have is two fermions coming in. One fermion, one anti-fermion, which is represented by this back arrow in the lower half, that exchange the fracton itself represented by this dotted line coming downwards. Now, again, this triangle that you see in the middle is actually the loop momenta itself. So what happens is that these two fermions and this anti-fermion come in, they exchange a scalar, which is, again, the virtual particle in this case, just like the two fermions were the virtual particles in the previous diagram. They exchange a fermion and they recombine to create one single fermion. And that's represented by this K1 plus K2 momenta particle that goes outwards. So in reality, what's happening in the physical sense, you have two fermion, anti-fermion coming in and a single fermion coming out. And what's happening inside, which is in this case is some kind of loop momenta, is the exchange of a virtual scalar, a virtual fracton, which then recombines to create this outgoing fermion. And again, this is a first order diagram because it has a single loop momenta corresponding to the exchange of the scalar momenta. Does that make sense?
Yes, that makes perfect sense. I'm just thinking about the way we would, let's say, strategically go about calculating something like this with the help of perturbation theory. I take it then that for the first term of this, or the base term, you would not really have an associated diagram to that, if I understand it correctly. And my follow-up question, if that is the case, is how do you actually get to computing the first term? Is that somehow unambiguously something you unambiguously would know without the help of any Feynman diagrams?
So you can compute this without the diagrams and just try to analytically look at the expressions. This was also done in the early stages of quantum field theory, where you would just write down these analytic expressions and compute them. But in terms of having a base term, I don't think you need a base term in the sense that you need a initial diagram which you have to go about defining the other diagrams. Once you have one diagram, you can construct all the other diagrams, and specifically once you have the Feynman rules, all the diagrams can be represented. So basically, it's a very general algorithmic approach, and it's, again, this is one of the beauties of perturbative quantum field theory, which is once you have these Feynman rules, once you have, and you can construct these diagrams. Once you have these diagrams and you have these Feynman rules, you can map each one of these diagrams to an integral, and these integrals then can represent some kind of relevant term in this kind of series expansion. And the series expansion is truly, again, you can show the equivalence between these by looking at what is known as a path integral representation of this quantum field theory, which is basically the framework of how we can interpret quantum mechanics more generally. And you can show that every series, every order term in the series expansion for the path integral actually does indeed correspond to one of these diagrams. And as long as you have one of these diagrams written down and their Feynman rules, independent of any kind of base term, you can actually compute them directly and find their relevant contribution to the series.
Okay, thank you.
Yeah.
Then the final term of the introduction that I would like to discuss is, or sentence, let's say, is when you say that you calculate the associated one-loop renormalization group flows for the coupling constants. Would you mind describing what that is, and then also why that's useful to know?
Yes. Okay. So now, why? So, what is renormalization group flow? So, one of the central components of quantum field theory is this notion of renormalization. Now, renormalization is a centerpiece of quantum field theory in that it's inherent to all quantum field theory. So, in the early stages of quantum field theory, what happened was that what would arise are these kinds of infinite-like divergences that would appear in these integrals. Now, typically in physics, when you have infinities, that typically means that physics at that level breaks down. The formalism that we have constructed effectively breaks apart in this higher energy regime. And this is prevalent throughout quantum field theory. Initially, in the context of quantum electrodynamics, this was present, but this undergirds the entire infrastructure of quantum of QFT more generally. Now, what a physicist by the name of Kenneth Wilson developed this notion of the renormalization group, meaning that he introduced the idea that these infinities are actually physical characteristics of the theory itself. And that what's happening is that once you integrate these energies at very high momenta or very short distance scales, which corresponds to very high energies based on the uncertainty principle, what happens is that the theory that we're considering breaks down at that level. So it's not that the physics that we're considering is wrong at the energy scale that we're interested in, but it's that the physics that we're explaining cannot explain the physics at all energy regimes. So what we're basically saying is that our physics is an effective theory at a very specific energy regime, and so all the physics that we can explain is in that energy regime. We cannot go higher. And so that is very important because that does not render our theories useless, but it constrains the physics that we can explain. And so the way we go about incorporating this notion in our equations is through renormalization. And that basically when we have these kinds of infinite-like divergences, we introduce what are known as regularization procedures that can remove these kinds of infinities in a very systematic way so that we can only capture the physics of the relevant scale that we're interested in. And specifically how that relates to what is known as the renormalization, and that's the notion of renormalization. Renormalization group flow is the notion of what happens to this renormalization at different energy scales. So not only can we characterize the physics at these energy scales, but this regularization prescription that we do use to solve these problems can be manipulated in a way such that we can construct a differential equation that shows the flow of this renormalization at different energies. So effectively, we have this kind of differential equation that shows how our renormalization changes as we go to higher and higher energy scales or lower and lower energy scales. And this is known as the renormalization group flow.
Okay, great. Yeah. I want to have a look at the formalism associated with the lattice that you actually describe, or the way you describe the system. Let me go to equation 2.4 here, because I think this gives a breakdown of the Hamiltonian that you describe in this lattice. And I take it that this is before you do the, where you take, or before you take the limit, where the density goes to 0, right? So would you mind describing what the terms of this Hamiltonian are, and let's say how important they are relative to each other? Like, are they all comparable in magnitude as well? Or are there like a couple of these that are more important than the last?
As I mentioned earlier, and as we had discussed, these continuum theories that we're ultimately interested in should hopefully describe the low energy physics of certain kinds of lattice systems. And so the way
Mhm.
we went about to motivate our analysis for this was to present a relevant lattice model that might be of interest and try to analyze its low energy continuum description. And so in this case, what you have are three very specific terms. You have this H scalar, H fermion, and H interaction. These H are represent the different Hamiltonian terms, which describe the energies of the systems of interest. So H scalar represents the Hamiltonian for the fracton, the scalar field. H fermion represents the Hamiltonian for the fermionic fields, and H interaction represents the Hamiltonian for the interacting fields. Now, each of these terms, the first two terms in the second line of equation 2.4, represent the terms for the scalar. This next two terms represent the terms for the fermion, and the last term represents the interaction between the scalar and the fermion.
Mhm.
Now, how are they important? Now, there comes a slight subtlety in how we introduce these, which is here phi of s, the phi and pi s are conjugate momenta fields. So pi s is a conjugate momenta field to phi s, where phi s can be thought of as the field representing the actual fracton itself. It's the excitation on this kind of lattice that we had discussed.
Mhm.
And the way we represent this as a quantum mechanical theory is to introduce these kinds of non-trivial commutation relations with the momenta field, which is this pi s field. So one of the centerpieces of quantum mechanics, the idea of quantum mechanics more generally, is the uncertainty principle, which says that one cannot know both position and momentum simultaneously, and this maps to the notion of operators in quantum mechanics more generally by having a non-trivial commutation relation between momenta and position. In the quantum
Mhm.
field theory case, this extends to the notion of position fields, the field itself, and its conjugate momenta field pi s. And
Mhm.
here pi s and s here represents the different sites on the lattice. Well, here, basically, what we're saying is that the total energy for these excitations corresponds to the momentum contributions coming from the field itself on the different lattice sites, plus this kind of interaction, this self-interaction term, this cosine delta xy of phi s, that comes
Mhm.
from a single loop around a lattice site, a plaquette of this field going around in a loop. And so
Mhm.
this is another kind of energy contribution that contributes to our system in this kind of lattice system for just the scalar itself.
Mhm. How does
And
the overall energy that we're describing now relate to
yeah,
the free energy that we were touching on before? Are these the same in this setting, or are we talking about two different quantities here?
so in the interacting case, the free energies are different because the energies are now, because of the coupling, the energy actually shifts. And so here the energy will be inherently dependent upon the strength of the coupling and so forth. And that's where the problem becomes very non-trivial and very non-analytic, because now you have to use very stringent approaches to try to solve for it. Without
Mhm.
the interaction, then these systems can be well defined. So, for example, if you remove the last interaction term and you have these terms independently, these can be just thought of as regular lattice systems that we can try to analyze. And
Mhm.
again, these problems independently are still very difficult to try to understand. But basically, this would be lattice dynamics for the fracton, and the second term of just the fermion, if it was uncoupled, would be lattice dynamics for non-relativistic fermions.
Mhm.
Both of these problems have been studied previously. They're somewhat well known, especially the fermion problem. There's an entire literature on it. But when you add the interaction term, specifically this last term, which is the interaction between the fracton and the fermion itself, then you get very highly non-analytical results in which in the lattice case, there are many different computational techniques you would have to use. But in our case, what we try to do is analyze it in the continuum case, where we instead look at it in the continuum theory and see if we can use
Mhm.
techniques of quantum field theory to understand it better.
Mhm. Okay, great. So let's move over to the section on of this continuum.
Sure.
And I think equation 3.6 here is, or well, 3.6 and 3.7
Yep,
are the, let's say, continuous equivalents of what we were looking at before.
that's
Is that
right.
right?
Yep, that's
Okay.
exactly right. So in this
Would you
case,
mind Yeah.
Yeah, sorry, go
Would you
ahead.
mind explaining the signatures that are associated with this and also what differentiates the two expressions?
Right. So in this case, what you have, as you had correctly mentioned, is the continuum models that for these kinds of lattice systems. Specifically, these systems, if we take the lattice spacing A, which represents lattice spacing in these theories before, to 0, our argument is that these theories represent their low energy dynamics. Um, and so what you have here is, instead of there being a sum over lattice sites, now you have a continuum, a field theory in which the fields spread over all of space-time, in this case in two spatial dimensions in one time dimension, and they are now quantum fields in that they are fields that exist on top of the space-time.
Mhm.
Now, the second part of what are these signatures, that comes down to trying to understand what kind of space-time are we in. So typically when we do physics, physics is typically done in Minkowski space-time, which is the space-time in which you have Lorentz transformations and this notion of boosts and time dilation and so forth. So in
Mhm.
physics, of course, we know there's ideas of special relativity in which we know that space and time are intimately connected, and in the way that we represent them on a manifold or in physics and generally is through Minkowski space, in which
Mhm.
time and space have a very unique metric signature corresponding to them. Now, the reason why that's unique is because that impacts the way we can do calculations and the way vectors transform and the way a lot of the mathematics that we try to analyze these systems and act.
Mhm.
However, Euclidean space is an alternative signature. Euclidean space, just like in Euclidean geometry, is a standard signature that we've come to know, which is the way we do standard vector addition, standard vector transformations. It's basically the same geometry that we all have an intuition for.
Mhm.
Basically, you can extend this in 4 spatial dimensions the same way you would do it in 3 or 2, but this is not the same as Minkowski space because Minkowski space is a very unique definition. However,
Okay.
mathematically, there's a transformation known as analytic continuation where you can transform mathematically from Minkowski space into Euclidean space. Now,
Mhm.
what that means is that the physics is still the same in that it's still all Minkowski space descriptions, but we've played a mathematical game in which we've transformed our system into Euclidean signature, a description in terms of Euclidean spacetime, which allows us a very concrete way of computing the integrals. So it's a mathematical construction that we've used, a mathematical transformation that we've used to actually solve the problems in a very clear and concrete way.
Okay. Do you make use of both of these formalisms in actually solving the problem, or is there one where sort of all the computations are done?
Yes, and that's we use the Euclidean signature to do all the computations. So
Mhm.
The Minkowski space equation 3.7 is used for completeness to show what the actual theory we're analyzing is.
Okay.
But 3.6, the Euclidean signature, the actual transformation that we do, is the signature in which we do all the practical computations.
Okay.
And the reason why we do it is because it greatly simplifies the kinds of integrals that we're interested in doing.
Mhm.
So for the purposes of the entire paper, all of the notation and all of the diagrams that we compute will be in Euclidean signature.
Okay.
Yeah.
Could we maybe say a few words on how applicable the extension is as well that we're doing with the lattice? So moving from this discrete case to
Mhm.
a continuous quantum field theory,
Yeah.
I take it that perhaps in this particular investigations there are in this particular investigation there might not be comparable previous let's say experiments or something that's been done to validate how good of an approximation this is. But in
Sure.
general, taking that limit, is that something that's been observed before as a prudent approach? Let's say that doesn't incur too many um, that doesn't incur too large errors in your theory, or do you have a view of how good that approximation tends to be?
Yes, so right. So lattice field theories in general is a very, very large literature. It started many decades ago in the 70s and so forth. And there's a lot of there are issues to it, but it's also very robust in that
Mm.
there's actually an entire field known as lattice quantum chromodynamics, in which basically people try to use these lattice constructions to explain quantum field theories that are actually non-perturbative. So back to our original discussion was what happens when we have these strongly coupled theories. The standard techniques of perturbative quantum field theory fall apart. And in those cases, what people had tried to construct is try to use these lattice constructions, which are basically putting these systems on a lattice to try to see if we can compute stuff, relevant physics that may not be computable in the perturbative picture. And in those
Mm.
cases, what you find are very robust results. Specifically, what you find is that You can indeed compute quite a lot of stuff. You can compute things like confining approaches to quarks and everything. But you also get many different problems. You get something known as a fermion doubling problem. There are a whole bunch of actual issues that you run into, which are still very present in the work itself.
Mhm.
But however, there are still areas that are well understood enough to the point where these continuum theories are still very descriptive of some of these lattice systems themselves. Now, for our particular case, these lattice systems have not been analyzed, at least not that I'm aware of, by some rigorous computational approach. But we're standing on top of the body of work that has existed of lattice field theories in general to try to make this robust comparison between the field theoretic approach, the continuum field theoretic approach, and the lattice approach.
Mhm. Okay, great. I want to make sure we have some minutes to discuss beta functions as well.
Sure,
So I
of
move
course.
to the chapter on beta functions now.
Yes.
Would you mind just describing what beta functions are? And then also,
Yes.
once we've done that, we can get to the figures that are on the screen now.
Right. So initially, as I had mentioned to you, renormalization group flows are basically this way of characterizing the change of the relevant physics based on the energy scale we're at. And the way that we actually do that is look at the relevant parameters of our theory. Now, parameters in our theory are generally known as coupling constants. These are constants that correspond to, for example, the strength of the interaction between the fracton, the scalar field that we had, and the fermion itself. This is a relevant parameter because this dictates to us how strongly coupled these different fields are. And the way
Mhm.
you can actually analyze them is in these kinds of different energy regimes is through this renormalization group approach, or specifically in terms of these beta functions. Now, these beta functions are basically functional representations of these renormalization group flows. Specifically, they are partial differential equations that represent the change of the coupling constant relevant to some energy scale. In this case, the energy scale being our renormalization prescription of the ultraviolet cutoff. In this case, what we're basically saying is that at a certain energy scale, we simply cut off the integral so we don't encounter this divergence. And this upper bound, this lambda scale that we have, basically corresponds to our RG parameter, our renormalization group parameter, which allows our coupling constants to flow. So the lambda can represent the different energy scales that we're at, and the relevant coupling constant will be a function of that energy scale. And from that partial differential equation, you can then solve the differential equation analytically or numerically and get different kinds of plots for them and see how the physics changes based on the relevant energy scale. And the
Mhm.
diagrams that you see right here are basically those diagrams exactly.
Okay.
Where,
And so
yeah, go
all of
ahead.
the beta functions, I believe, originate then from this equation 5.1, which is sort of the general formalism, and then you have the specific ones, the specific solutions to the partial differential, or well, rather the partial differential equations themselves in
Yes,
5.2 here. Okay.
yes, exactly. That's right.
What does it mean for the beta function to vanish? So I guess one of the key findings is the related to the beta finding of this lambda,
Yes.
which I would let you explain now. But could you please, in doing so, also explain what it means for the beta function to vanish?
Right. So in this case, what happens is that, as you had pointed out, 5.2 represent these partial differential equations that represent the flows of the relevant coupling constants. Now, what it means for a beta function to vanish is to mean that the beta function actually equals zero. Now, what
Mhm.
does that mean? If it equals zero, what that basically means is that the parameter itself does not change as you change the relevant energy scale. Now, that's very important because that means your theory is scale invariant, meaning that
Mhm.
irrespective of how strong how high the energy is or how weak the energy is, the coupling constant will be the same. So you can be in a regime in which the energy is very high, the distance scales are very, very short, and the coupling strength between the two fields will not be different. This is a very counterintuitive thing because in a more conventional theory like quantum electrodynamics, a theory of electrons and photons, you have a coupling constant that grows. As you get closer,
Mhm.
two electrons get closer, the strength of their interaction grows, and so they become more repulsive. Similarly, as they go farther away, the force becomes weaker and they decrease as they go farther away. What this is
Mhm.
basically saying is that if you have a fermion and a fracton, as you get closer and closer or farther and farther away, the strength of your coupling will not change. It will be the same.
Mhm.
And this is a very unique characteristic of the underlying physics. And so what we have found is that from a computational standpoint, from just first loop order, you actually see that there is indeed a vanishing. And what we show later on is that we can actually use a very non-perturbative technique known as a ward identity to show that in any order in the perturbative series, any order in the series expansion, all of these terms will vanish, and you will actually have this beta function equals 0 to any order of the perturbative series, which is a very unique, non-trivial result that we would not have expected.
Mm-hmm.
Does that make sense?
Yes, it makes sense. I'm trying to wrap my head around what that means conceptually. Like,
Sure.
saying now that we have a interaction strength that doesn't vary based on the scale of the system. Do you
Yeah.
potentially have any examples of where that occurs, like in other systems that you might be able to or that I might be able to relate to more?
Sure. So one of the biggest theories that have this are known as conformal field theories. So conformal field theories is a very big branch of physics in itself, in that these are theories that have conformal symmetry, which are basically symmetries that leave angles invariant. So if you have two vectors, a conformal transformation would basically transform these two vectors in a way that preserves the angle. Now, these conformal field theories are basically composition. One part of the conformal group is actually the scale invariance that we find. Now, these conformal field theories more generally explain fixed points, so points between phase transitions in physics. So, for example, if you're going from in condensed matter physics, for example, you have something known as second order and first order phase transitions between, say, solids and liquids to gases, and you have many different kinds of transitions between superconductivity and other kinds of phases of matter. Now, in the actual point of transition, the point at which this one phase of physics goes to a different phase of physics, you have the idea of a fixed point. And in that fixed point behavior, this specific point, the specific energy scale, what you can actually describe this physics is by a quantum field theory like this. And specifically, the quantum field theory that you would describe it by is in some cases, by a conformal field theory, or a theory that has this kind of scale invariance. And the reason why that's important is because at these phase transitions, basically what you're saying is that as you get shorter or farther away from the relevant physics, the coupling constant stays the same. And that's a very unique property of the physics at this very specific phase transition. So these scale invariant properties are very abundant in these fixed points, and so you'll see them in many different ways at those in those kind of situations. And so that's one area where you get scale invariance.
Yeah, thank you for elaborating on that.
Sure.
In terms of identifying the symmetry, how did you
Yeah.
find it? Did you stumble upon it numerically when you ran these calculations, or like was there is there a particular strategy for trying to identify symmetries like these in these kind of systems?
Yes. So typically, a zero is a very unique number in physics in general. And when you get zero, that typically means that something happens. Typically, you don't get zero out of coincidence. And
Right.
so, especially in beta functions or especially in loop calculations, when you get zero, in this particular case, the reason why you get zero is because there's an exact cancellation between this minus delta lambda plus this lambda delta z psi. Now, there is no reason why these two things should cancel arbitrarily. It would be very strange if they just canceled like that. So typically that gives you some motivation to try to find some kind of underlying symmetry that enforces this kind of vanishing characteristic. And so once we had found this vanishing loop computation, initially once we did it, we actually found it was non-zero, and then once we corrected our computation, we did find it was zero, and that led us to actually trying to compute or trying to find the symmetry. And once we tried to analyze it, it took us some time, but eventually we were able to find this very unique hidden symmetry for this system that would actually enforce what is known as ward identity of this vanishing beta function for lambda. And that's what you see in this equation 5.3, which is a very specific, unique transformation of the field psi and phi itself that lead to this very specific ward identity of the first vanishing term of 5.2 to all orders in the perturbative series.
Okay.
Yeah.
We're quite short on time now. We have
sorry,
we have a few minutes left. So before we run over time, I just want to ask if there are any other parts of the results of this investigation that you would like to present. Just things that you found here that you think are worth mentioning before we bring the interview to a close.
Yeah, so I think overall the main we discussed the main ideas, which is one, what is the relevant physics, the idea of the beta functions and the vanishing beta functions and the word identity. I think that is all good. I think what basically to conclude, what is the big takeaway from this paper? One is that the this idea is that the theories that we had considered, these continuum theories for the fractons themselves, have very strange properties. Specifically, they have properties of things like UV-IR mixing. They have properties of these kinds of infinite subsystem symmetries. They have many of these kinds of properties that are very non-trivial and very strange and very particular to this kind of physics. And so our approach, our big takeaway was that once we tried to analyze this perturbatively in this kind of quantum field theory approach, there was a lot of reason to believe that this wouldn't actually have some kind of clear continuum definition. And that if we try to use standard techniques of perturbative quantum field theory, that there would be some kind of apparent restriction that stopped us from doing it because of the strange behavior of the physics itself. What we found is that that is not indeed the case. That what you do, you can actually do standard perturbative quantum field theory, analyze these systems in a systematic way, and get very concrete results that tell you things about the renormalization group flow, the beta functions, and their Feynman diagrams, which is a very unique and unique approach, because now what that tells us is that if we want to analyze any other aspect in perturbation theory, we can. And perturbative quantum field theory is a very broad framework, so that gives us an incredible tool to understand them. Outside of that, this word identity is also indicative in telling us that there's some underlying physics that we can try to understand, that there's hidden symmetries that give us great leverage in constraining these systems. And so this inherent fracton properties actually give us incredible leverage in trying to understand the physics itself. So it's worthwhile to see what does that mean down the line about what other kinds of properties can constrain. And then I guess finally, this last point I'll mention about these systems that is a big takeaway is the idea of this UV-IR mixing and this idea of renormalization. This renormalization prescription that we used was a very particular one, in that typically renormalization in this Wilsonian definition of renormalization assumes that we can remove the ultraviolet divergences, these infinite-like divergences at very specific length scales. The physics that we see here is that that is not always the case. What we find is something known as we find a UV-like divergence specifically at very large length scales, which is in the IR regime, the infrared regime. Now, this is a very big problem in field theory in general, because our Wilsonian notion of renormalization is a standard way that we understand quantum field theories in general. And so what we do find is that this UV-IR mixing, which was present in the original fracton continuum theory, also persists in the continuum theory. So a big area of research, a big area of inquiry would be, how do we resolve this issue? What can we understand about this? And are there any kind of unique or alternative renormalization prescriptions that we could use that could try to shed light on this kind of inherent issue that we find? Or is this UV-IR mixing just so inherent to the physics that we have to try to understand that better and try to construct some kind of physical understanding of what that means? So this is a big open-ended question of how do we understand this renormalization of these theories in a very concrete way?
Okay, very good. Thank you very much for all the insights throughout the interview and for tying it up in such a nice way. I'm happy here, so I think we can close the interview. Just thanks for taking the time to do it.
Of course, yeah. Thank you for having me.